You're going to have to just take the derivative. Huh? Yeah, so good question. So the question is, why do the 3 and the 1, 6 stay and they don't become zeros like the natural log of 4 became a 0? And so it's just a matter of, thinking back to our properties that we introduced in the beginning. I'm blanking on section numbers right now, but 2.3 is when we started talking about this introductory derivative rules. But if you're thinking about it, it should make sense, because if I'm dealing with a constant by itself, if I were to graph the function f of x equals 10, what would that look like? If I were to graph f of x equals 10, it would be a horizontal line, okay? So a constant by itself, if you're looking at the graph of a constant by itself, it's a horizontal line. The derivative is the slope, and we know the slope of a horizontal line is 0, okay? So that's why that when a constant is by itself, it becomes 0. On the other hand, when a constant is a coefficient of a function, you can think of it, like 3x. If I was thinking about graphing 3x, that would be a line that has a slope of 3. And so the derivative of that needs to be 3, right? So it's just a matter of a difference of multiplying by a constant versus adding a constant by itself. And so really think about those two different horizontal line versus the coefficient representing the slope. Good question. All right, so let's look at some of these applications. So if f of x is a differentiable function with f of 0 equal 1 and f prime of 0 equals 2, what is g prime of 0 if g of x is equal to 4 f of x plus x squared, all raised to the 8th, all divided by e to the x? Okay, so for the sake of time, I am just going to jump in and find the derivative without defining things out. And so I apologize if it helps you to kind of define things out, but I'm just going to jump straight in. Okay, so our big picture here is, so that the only difference between this and what we were dealing with in our other problems is now we have this unknown function that's a part of g. Okay, that's the only difference. Other than that, it's the same as we've already seen. So my big picture here is I'm dealing with what? A quotient, okay? And so I'm going to have to use the quotient rule. So that tells me that I'm going to use the quotient rule. So it's going to be my bottom function, e to the x, times the derivative of the top function. Well, that top function is a composite function. So to find the derivative of the top function, I'm going to have to use the chain rule. We have a function raised to the 8th power. The 8 comes down in front. The function on the inside remains the same. We subtract 1 from the power. So 8 minus 1 gives us 7. And then we multiply by the derivative of the inside. My inside here is a sum of 2 functions. So I can find the derivative of each piece and leave the sign in between. The derivative of 4f of x is just going to be 4f prime of x. Plus the derivative of x squared is just 2x. Okay. So this right here is the bottom function times the derivative of the top minus the top 4f of x plus x squared to the 8 times the derivative of the bottom, the derivative of e to the x is just e to the x, all over the bottom squared. So I used the quotient rule, and then within the quotient rule, when I got to the point of finding the derivative of the top, I used the chain rule. So now we're asked to find g prime of 0. So g prime of 0, I'm going to replace every occurrence of x with 0. So e to the 0 times 8 times 4f of 0 plus 0 squared raised to the 7th. We have to be really careful with our parentheses here. Times, open parentheses, 4f prime of 0 plus 2 times 0, close parentheses, close square bracket, minus 4f of 0 plus 0 squared raised to the 8th times e to the 0 over e to the 0 squared. All right, so we are told that f of 0 is 1. So every occurrence of f of 0 we can replace with 1. And then we are told that f prime of 0 is 2. So every occurrence of f prime of 0 we can replace with 2. Okay, so what does this become? So what's e to the 0? E to the 0 is just 1. So we have 1 times open square bracket, and we have this 8. To simplify what's inside these parentheses. So 4 times 1 is 4 plus 0 squared. So 4 plus 0 is 4. So 4 to the 7th. Times inside these parentheses, we have 4 times 2 is 8 plus 0. So 8. Close that square bracket. Minus 4 times 1 is 4 plus 0 is 4. So 4 to the 8th times e to the 0 is just 1, all over e to the 0 squared, which is just 1. Okay. Sorry, what I have written on my page is correct arithmetic. So we have 8 times 4 to the 7th times 8 minus 4 to the 8th gives us 983,040. Yes. Yeah, so it just basically is, it has to tell us that for us to be able to find f prime of x, right? So for it to be differentiable just means that it has a derivative, okay? So if it didn't tell us that it was a differentiable function, you know, it could technically be some really crazy function that has lots of discontinuities or lots of sharp corners or things like that, but that's just telling us that for every value of x, we can define the derivative. Yeah, it's just telling us it's a nice function. Good question. Okay, so I really want to make certain that we talk about implicit differentiation. So if you had to pick between these 3 applications left, 11, 12, and 13, is there one in particular that you would like me to work? I'm going to work one of those. 11, 12, and 13. Anyone have a preference? 11? Okay, let's do 11. And then I'll just write up the solutions for 12 and 13, but I want to be able to talk about implicit differentiation. Okay, so 11, find the equation of the line tangent to the curve of f of x equals the following. All right, so we can do a little bit of rewriting with our function. All right, so anytime we see a radical, we need to rewrite it as a power function. So this would be 32x squared raised to the 1/9. So again, be careful here. It might be really tempting to just apply the 1/9 to the x squared, but it's not, right? Because that 32 is inside there. So I'm going to leave this as the whole thing, 32x squared raised to the 1/9. And then plus, we could apply our derivative rules as this is initially written. But as it's initially written, it's written as a composite of 3 functions, right? So the outer function is the natural log of x. The middle function is x cubed, and then the innermost function is x minus 3. And so to avoid having to use the chain rule within the chain rule, we can use our properties of logs. Remember, if we have the entire inside of a log raised to a power, that power can be brought down in front. So 3 times the natural log of x minus 3. Okay, so what we're using here is properties of laws. Okay, so here is our slightly rewritten function. And so if we're wanting to find the equation of the tangent line, the first thing we need to do is find the slope of the tangent line. And how can we find the slope of the tangent? Okay, so we need to find the derivative, and then we're going to evaluate the derivative at x equals 4. So we need to find f prime of 4. All right, that's what we're trying to find. So we first need to find f prime of x. We see my function is written as a sum of two functions, so we can find the derivative of each piece and then leave the sign in between. I'm going to go through my whole bag of cough drops so I don't have another coughing fit. Okay. All right, so slope of the tangent line, that is f prime of 4. Okay, so f prime of x, we find the derivative of each piece and leave the sign in between, but each piece we see is a composite function, right? So instead of having x to the 1/9 for that first function, we have 32x squared to the 1/9. And so that 1/9 comes down in front, the 32x squared remains as is. We subtract 1 from the power, 1/9 minus 1 gives us negative 8/9. And then we multiply by the derivative of the inside. The derivative of 32x squared is 64x. Plus the derivative of 3 natural log of x minus 3. Again, that is a composite function. Last week we talked about finding the derivative of the natural log of x. Now we're being asked to find the derivative of the natural log of x minus 3. So we have to incorporate the chain rule. Derivative of the natural log of x minus 3 is going to be 1 over x minus 3 times the derivative of x minus 3, which ends up being just 1. Okay. So then we want to evaluate this at 4. So we have 1/9 times 32 times 4 squared raised to the negative 8/9 times 64 times 4 plus 3 divided by 4 minus 3, if I combine all that together. If we do this, I'm not going to take the time to type this all in. But it ends up being 2. It looks like a mess. But 32 times 4 squared nope, it doesn't end up being 2. I lied. I'm looking at the wrong thing. Apparently need glasses. Okay, so it ends up being 28/9. Did anyone take the time to type that in? I'm pretty certain it ends up being 28/9. If it doesn't, you can let me know. Okay, so this is the slope of the tangent line. How do I find the y-coordinate of the point that the line is passing through? Okay, so before we get into finding the equation of the line, we need to have a point, right? This is our slope. This is our m. Right. So we're going to plug x equals 4 into the original function. So to find the y-coordinate of the point, we need to find f of 4. So I'm going to plug that into my simplified function. So 32 times 4 squared raised to the 1/9 plus 3 times the natural log of 4 minus 3. And this is what comes out to be 2. Okay, so now we can find the equation. Because we have a point 4, 2, and we have a slope 28/9. x. And so we can use, like you said, y equals mx plus b. Or we can use y minus y1 is equal to m times x minus x1. I'm going to use the second one. So we have y minus 2 is equal to 28/9 times x minus 4. So I'm just plugging in the y coordinate of my point for y1, plugging in my slope for m, plugging in my x coordinate of my point for x1. That's technically an equation of a line, but if we want to solve it for y, we could distribute that 28/9. So we have y minus 2 is equal to 28/9 x minus 28/9 times 4. Add 2 to both sides, we get y is equal to 28/9 x minus 28/9 times 4 plus 2 gives me minus 94/9. And so that would be the equation of the line that is tangent to this curve at x equals 4. All right, so I'm going to skip over 12 and 13. They're just some more applications similar to what we saw last week. Just the only difference is now we're having to use the chain rule to find the derivative, but the application itself is fairly similar. One thing I will mention on 12 really fast, I believe this is similar to a computer homework problem. So we have to remember that if we're dealing with continuously compounded interest, we have A of t is equal to p to the RT. And the main thing to keep in mind is that you don't want to plug in t initially. So you want to find your function, take the derivative, and then plug in t. Okay? And so I'll mention that. But then 13 is very similar to what you saw last week. Okay, so in 2.6, you saw there's 2.6 really could be split into two sections. So the first half of 2.6, you looked at implicit differentiation. The second half of 2.6, you looked at those related rates word problems. So we will talk about the related rates word problems next week, but I wanted to talk a little bit about the first half, implicit differentiation. Okay, so when we're looking at implicit differentiation, this idea is needed when solve for y, right? So in everything we looked at in all these problems we're looking at, we had it, the function was given as y is equal to a function of x, right? So, you know, we didn't always call it y, but, you know, on the right-hand side, we had a function involving the independent variable, and then the dependent variable was on the left-hand side, right? We didn't have both the independent and the dependent variable mixed throughout the equation, okay? And so the need for implicit differentiation is when we can't do that. We can't solve the equation for y, and so it gives us a way to find the derivative without having or without being able to solve the equation for y. So instead of reading through this, I'm just going to jump in to a problem. Okay, so like if we look at 14, we have x's and we have y's on both sides of the equation. In all the problems today, we've had y on the left-hand side and then a function of x on the right-hand side. Okay, so when we are dealing with something like this, we can use implicit differentiation, which just means we're going to take the derivative with respect to the independent variable, which typically is x. We're going to take the derivative with respect to x of both sides of the equation. Okay, so one thing we need to do here is remember that we want to rewrite radicals as power functions. So the cube root of y would be y to the 1/3. Okay, so the first step of implicit differentiation is to take the derivative with respect to x of both sides. Okay, so now realize that what I'm writing here, this d over dx, this is not, that's not the derivative, okay? So that's different than writing dy dx, right? So they look very similar, because one has a y, one doesn't have a y, but they're different. This is the derivative. This is telling you to take the derivative of what's inside. So if it confuses you to write this first line, don't write the first line. But I'm not saying I'm multiplying everything by the derivative. I'm saying this is an operator. I'm telling you that I am going to take the derivative of everything that's on the inside. So I'm going to take the derivative of the left-hand side. And I'm going to take the derivative of the right-hand side. Okay, so all I did there is I'm telling you what I'm about to do. And again, if you read that as the derivative times something, that is wrong. It's telling you I'm going to take the derivative of what's on the inside. Okay, so on the inside, we have, on the left-hand side, we have a sum and difference of three functions. So we know to find the derivative of a sum or difference of three functions, I can just take the derivative of each piece. What's the derivative of 7x? 7. Minus, what's the derivative of 14 e to the x? 14 e to the x. Plus, and then this is where we have to be careful. So when I am doing implicit differentiation, if I am taking the derivative of an expression involving just x, I treat it just like I did previously, right? Nothing special whatsoever. I'm just applying my derivative rules. But when I get to an expression involving y, I have to keep in mind that y is a function of x. And so when I don't know what it looks like, right? If I did know what it looked like, I would have solved the equation for y. I don't know what it looks like, but I know is y is a function of x. And so when I find the derivative of an expression involving y, I have to use the chain rule, okay? So think about this. So I don't know what y is. So if I asked you to take the derivative of something like 7x squared plus 4 raised to the 1/3 power, hopefully you would all be pretty comfortable with that at this point in time, right? We've done that quite a bit today. So what is the derivative of 7x squared plus 4 raised to the 1/3 power? What would I do? The 1/3, leave the inside alone. Right, I subtract 1, so 1/3 minus 1 would give us negative 2/3. Times 14x, okay? So I think hopefully we are all comfortable with that by this point in time, okay? So that is the idea I'm using over here. I just don't know what y is, right? And so this right here, this is what I'm calling y. Okay. And then this right here is the derivative of y. So this right here is what I'm calling dy dx. Okay. So when I come back over here, I'm taking the derivative of y to the 1/3. The derivative of y to the 1/3 is going to be 1/3 y to the negative 2/3, right? 1/3 y to the negative 2/3. And then we have to multiply by the derivative of y, which we're going to use dy dx to represent the derivative of y. Yeah, you can write y prime instead of dy dx. The one why we get you on the habit of doing this here in the first half of 2.6 is because in the second half, you know, there are lots of variables going around, and so we want to make certain that we are clear on what we're taking the derivative with respect to, right? If we write y prime, we don't know whether that's dy dx or dy dt. And so when you get into the implicit differentiation problems, it's a good habit to begin to write dy dx. But yes, if it helps you on these problems to write it as y prime, you can totally write it as y prime. Okay, but does everyone understand that what we did right here is we just use the chain rule, just like we did the first half of today. The only difference is we know y is a function of x, we just don't know what that function looks like. And so we treat it just like we did over here. So when you're dealing with implicit differentiation, you can always keep this that's more familiar in the back of your mind as you go through and find the derivatives. Okay, so then we do the same thing on the right-hand side. So the right-hand side has a sum and difference of 3 functions. We can just find the derivative of each piece. The first is just y. So the derivative of y with respect to x is just dy dx. We don't know what that is. We can just write that symbolically. Minus the derivative of 2x squared. That doesn't involve the y, so we can just use our standard rules. The derivative is 4x. Plus the derivative of a constant by itself is just 0. Okay, so with implicit differentiation, there is one line of calculus, and then the rest of it is just algebra. Okay, so this is our one line of calculus. The rest is algebra. So once we do that one line of calculus, then we just need to solve for dy dx. So we look for all the terms that have a dy dx in them. So on the left-hand side, one term has a dy dx in it. On the right-hand side, one term has a dy dx in it. So we're going to move everything that has a dy dx in it to the left-hand side, everything that doesn't have a dy dx in it to the other side. All right. I'm trying to decide to what extent I want to show this. So I need to subtract dy dx from both sides. And then I need to subtract 7 and add 14ex to both sides. So on the left-hand side, I would have 1/3 y to the negative 2/3 times dy dx minus dy dx. And then on the right-hand side, I would have minus 4x minus 7 plus 14 e to the x. Everything that has a dy dx in it to one side, everything that doesn't have a dy dx in it to the other side. Then we factor out a dy dx, right? So we have these two terms on the right-hand side. If I factor out a dy dx, I'm left with a 1/3 y to the negative 2/3 minus 1. The right-hand side remains as is. Come over here. This is kind of my thought bubble. Come over here, solve for dy dx. So if I divide both sides by what I have in parentheses on the left-hand side, I end up with dy dx is equal to negative 4x minus 7 plus 14 e to the x, all divided by 1/3 y to the negative 2/3 minus 1. We are able to find the derivative of y with respect to x without knowing what y is as a function of x. So we can find the slope of the tangent line to the curve of this graph without even knowing what y is. Yes, James?
How did you get the -1?
So the -1 came from right here. So if you're looking at, are you good with this line that I have written here?
Yes.
Okay. So when we got that line, the next step was to look at these two terms and factor out a dy dx out of both of these terms. So if I pull a dy dx out of the first term, I'm left with this 1/3 y to the negative 2/3. If we pull a dy dx out of the second term, I'm really left with like a 1 that was right there.
Okay, I get it.
Question. Other questions? All right, so let's look at a couple more. All right, so if we look at this next one, we need to do a little bit of rewriting. This square root of y is just y to the 1/2. We see that we have this equation that's involving both x and y. There's no way to solve it for y. So we're going to have to use implicit differentiation. Sorry, I can tell that I don't have another cough drop. I must start coughing again. So my tongue is numb, but we're not coughing, so that's good. All right, so let's take a look at this. So we're going to take the derivative with respect to x of both sides. So 5e to the 2x minus 4y to the 1/2. And then on the right-hand side, we're taking the derivative with respect to x of 3x squared minus 5 to the y. Okay, so on the left-hand side, you see we're dealing with a difference of two functions. So we can find the derivative of each term and leave the sign in between. In finding the derivative of 5e to the 2x, that is just involving x, so we can use our regular rules, right? So we can just, that's like as if it was written in the first half of this section. So to find the derivative of 5e to the 2x, what am I going to have to use? Chain rule, right? Because it's not just the derivative of e to the x, it's the derivative of e to a function of x. So that's going to be 5e to the 2x times the derivative of 2x, which is just 2. Okay. Minus finding the derivative of 4y to the 1/2. We see that that is involving a y. We're viewing y as a function of x. So to find the derivative of y, we have to use the chain rule. So kind of think about what we had up there written in that little thought bubble. So it's like having y to the 1/2. Okay, so we have that 4 out in front, and then we have a function raised to a power. That power comes down in front. The function remains as is. We subtract 1 from the power. 1/2 minus 1 gives us negative 1/2. And then we have to multiply by the derivative of the function. So we don't know what it is, but the derivative of y with respect to x. On the right-hand side, again, we have a difference of two functions. We can just find the derivative of each and leave our sign in between. To find the derivative of 3x squared, it's just involving x. That's easy. We can use our ideas from previous problems. Derivative of 3x squared is just 6x. Minus to find the derivative of 5 to the y, since we're taking the derivative with respect to x and treating y as a function. This is a composite function where 5 to the x is our outer function and y is our inner function. So this would be the natural log of 5 times 5 to the y. That right there is the derivative of outside evaluated at the inside. And then we would need to multiply by the derivative of the inside, so the derivative of y with respect to x, which is dy dx. Okay, so again, this is our one line of calculus. One line of calculus. The rest is just algebra. Okay, so we look at the terms that have a dy dx in them. So we have one term on the left-hand side that has a dy dx in it, one term on the right-hand side that has a dy dx in it. I'm not going to write, I don't want to write all the details, but we're rearranging a lot of things, right? So we are adding the natural log of 5 times 5 to the y times dy dx to both sides. And then we are subtracting 10e to the 2x from both sides, right? 5e to the 2x times 2 is just 10e to the 2x. So these cancel out on the left-hand side. This cancels out on the right-hand side. and we're left with minus 2y to the negative 1/2 times dy dx plus the natural log of 5 times 5 to the y times dy dx. And then on the right-hand side, we have 6x minus 10e to the 2x. Okay. And so then both of my terms on my left-hand side now have a dy dx in them. So I'm going to factor the dy dx out in front. If I factor a dy dx out of this first term, I'm left with a negative 2y to the negative 1/2. If I factor a dy dx out of my second term, I'm left with plus natural log of 5 times 5 to the y. The right-hand side is 6x minus 10e to the 2x. And then now I can divide both sides by what I have in parentheses. So I have dy dx is equal to 6x minus 10e to the 2x divided by negative 2y to the negative 1/2 plus the natural log of 5 times 5 to the y. This is on 15. All right, so 16, we have 3x e to the y, 7x squared y cubed is equal to 10. There's no easy way to solve that equation for y. So if we're wanting to find the derivative, we have to use implicit differentiation. So we're going to take the derivative with respect to x of both sides. Taking the derivative of that right-hand side is nice and easy. Taking the derivative of that left-hand side is not. Okay, so if we look at the left-hand side, we see we're dealing with a difference of two functions. But unfortunately, we see that each of those functions that we are subtracting is written as a product. So I'm going to view this 3x as my first function and this e to the y as my second function. And then likewise, when I get to finding the derivative of that second term, I'm going to view 7x squared as my first function and y cubed as my second function. So I'm going to have to use the product rule twice. So I have my first function, 3x, times the derivative of e to the y. So again, I'm taking the derivative with respect to x, but that expression is involving y. So I know I have to use the chain rule, right? Because I'm viewing y as a function of x. So the derivative of e to the y would be e to the y times dy dx. Okay, so this is my first times the derivative of the second, plus the second e to the y times the derivative of the first. In finding the derivative of 3x, it's just involving x. I can use my old rules. The derivative of 3x is just 3. Minus, I'm going to put in open parentheses, and then I'm going to apply the product rule, where 7x squared is my first function and y cubed is my second function. So in using the product rule, the first is 7x squared times the derivative of the second. I'm finding the derivative with respect to x, and this expression is involving y, so I have to use the chain rule. So that is like taking the derivative of a function raised to the third power. The 3 comes down in front. The inside remains the same, y. We subtract 1 from the power. So the derivative of the outside evaluated at the inside is 3y squared times the derivative of the inside, the derivative of y with respect to x is dy dx. So we have the first times the derivative of the second plus the second y cubed times the derivative of the first finding the derivative of 7x squared is using our old ideas. Derivative of 7x squared is just 14x. Close parentheses. And then the derivative of a constant by itself is just 0. Okay, so we need to do a little bit simplifying. So, but again, this is our one line of calculus. One line of calculus. Okay. So really I need to distribute this negative sign is the main thing that needs to occur here. I'm gonna do a little bit of rewriting. So 3x e to the y times dy dx. I'm gonna put this 3 in front, so plus 3 e to the y. I'm gonna distribute that negative sign and combine those constants. So 7 times 3 is 21, so minus 21x squared y squared times dy dx. And then if I distribute that negative sign, I have minus 14xy cubed is equal to 0. So we see that on the left-hand side, we have 2 terms that have a dy dx and 2 that do not. So I need to move the 2 that do not have a dy dx in them to the right-hand side. So subtract 3 e to the y and add 14xy cubed to both sides. Up here, so I have 3x e to the y times dy dx minus 21x squared y squared times dy dx equals minus 3 e to the y plus 14x y cubed. And then I can factor out a dy dx out of both terms on the left-hand side. If I factor a dy dx out of this first term, I'm left with a 3x e to the y. If I factor a dy dx out of the second term, I'm left with a minus 21x squared y squared. My right-hand side remains as is. And then I solve for dy dx by dividing both sides by what I have in parentheses. So I end up with negative 3 e to the y plus 14xy cubed divided by 3x e to the y minus 21x squared y squared. And so again, we're able to find an expression for the derivative without knowing what y is as a function of x. Okay, so I'm going to do one more problem. I'm running out of time. Let me 18? Okay, yeah, we can do 18. Let me just tell you on 17 that if you try to apply implicit differentiation as written, you would have to use the quotient rule. I think you saw one like this in your notes where sometimes it might be beneficial to rewrite the function first. So on this one, I would recommend multiplying both sides by this e to the y plus 7. So you get 3x squared minus 4y is equal to x times e to the y plus 7. And so then you could just use the product rule on the right-hand side instead of the quotient rule. But I'll go ahead and look at 18. Okay, so 18 says evaluate, and if you need to leave, that's completely fine. So evaluate dy dx at the point 1, 0. So again, we're needing to find the derivative with respect to x. So we take the derivative with respect to x of both sides. Enjoy y'all's fall break. Okay, so we take the derivative with respect to x of both sides. On the left-hand side, we'd have dy dx. On the right-hand side, we see we have a composite function. The natural log of x is our outer function. 10x cubed minus 4y to the 5th is our inner function. So we have to use the chain rule. So that would be 1 over the inner function. So 1 over 10x cubed minus 4y to the 5th times the derivative of that inner function that inner function is the difference of two functions. And so to find the derivative, we just find the derivative of each piece, leave the sign in between. The derivative of 10x cubed is 30x squared minus the derivative of 4y to the excuse me. So that's a expression involving y. And so we need to use the chain rule because we're taking the derivative with respect to x. So that is like 4 times a function raised to the 5th power. So that 5 comes down in front. So 4 times 5 gives me 20. The inside remains the same. So y remains the same. We subtract 1 from the power. So 20y to the 4th. And then we multiply by the derivative of the inside, which would be dy dx. All right, so that's our one line of calculus, right? So one line of calculus. And so then we need to solve for dy dx. And so we can do everything we have written here as being in the numerator. So the only way I'm going to be able to get this dy dx by itself is to get rid of this denominator. So I'm going to multiply both sides by this 10x cubed minus 4x to the 5th. So we have dy dx times 10x cubed minus 4y to the 5th is equal to 30x squared minus 20y to the 4th times dy dx. Okay. So on the left-hand side, we already have the dy dx kind of factored out of those two terms. We need to get this dy dx term to the left-hand side as well. So we can add 20y to the 4th times dy dx to both sides. In doing that, we would have dy dx times 10x cubed minus 4y to the 5th plus 20y to the 4th times dy dx. And on the right-hand side, we'd have 30x squared. Okay, and so we need to pull the dy dx out in front, right? So if I pull the dy dx out of this first term, I'm left with 10x cubed minus 4y to the 5th. If I pull the dy dx out of the second term, I'm left with a plus 20y to the 4th. My right-hand side remains unchanged. And then my dy dx can be solved for by just dividing through what I have inside those brackets. So we have 30x squared divided by 10x cubed minus 4y to the 5th plus 20y to the 4th. And then we're wanting to evaluate this at the point 1, 0. And so we would just be plugging in 1 for every occurrence of x, so 30 times 1 squared over 10 times 1 cubed minus, we'll be plugging in 0 for every occurrence of y. And so we end up with 30 divided by 10, which gives us 3. So really, when you're dealing with implicit differentiation, again, it's one line of calculus, and then it's really the algebra that gets us on the rest of it. Okay, so those few problems that I skipped over, I will write up those solutions, and those will be posted to the Math Learning Center's webpage by tomorrow. Again, next Tuesday we will, even though it's the last day of fall break, I will still be here, and we'll be reviewing 2.6 Part 2, 3.1, and 3.2. So if you can't come in person, you're more than welcome to join via Zoom. And then the next week we'll be doing your exam 2 review. So if you have any quick questions, feel free to ask. Otherwise, enjoy the rest of your evening. Sorry for coughing into the microphone. Yes.